first of all, I'd like to thank the organizers. And secondly, I'd like to thank Yuval because he allowed me to switch my talk with his talk, so thank you very much. I will take an idea that Professor, I'd like to help you pronounce that name. So maybe I'll take 2 minutes and let's see if it works. If it works, good. Otherwise, so you will get an idea of this place. Yes.
See a real need for a metro line connecting Netyatinkara, Nedumangad, and Attingal to Thiruvananthapuram.
So that's how you pronounce
you're in
it.
the next city when you reach the end of the sign displaying the name of the previous city. I've just got to call Shashi.
So this is exactly where our institute is. And as you see, it's very famous. It appeared in a late night talk show in US. It's called the Colbert Report in 2009. So it's much, it almost came at the time our institute was coming up. And so now you know how to pronounce that. Anyway, it's still a longer video. You can go look at it. He says that the way you know how you get to the next station is when you are done reading the sign of the first one, you get to the next station. That's the continuation of the joke. But I think it's pretty, as long names go, it is very small actually. It's only 18 alphabets. Perhaps New Zealand has one which has 85. This is perhaps the longest one. And things like this are anyway there in many German towns. I think Neckar-Bischofsheim might be exactly 18 letters. Anyway, so I'll tell you the problem. So I'll tell you about the exponent conjecture. I will tell you the history. And after telling you the history, maybe I'll sketch the idea or how one might approach the conjecture. So first, just the history, then some of our contributions, and then the sketch of, idea of the proof. I think I do this, yes. Let G be a finite group. Exponent conjecture says, does the exponent of the Schur multiplier, the second homology group of G with coefficients in Z, divide the exponent of G? This is the question. So at some point when I want to write, I would just use this notation for the multiplier. I will just use this notation. Okay, so later if I forget to write that, this is, at the beginning I'm denoting it that way. Now, the exponent, by exponent means the smallest integer, so our groups anyway, smallest integer n such that G to the power n equal to 1 for every element of G. That is what I mean by the exponent of a group. We are only working with finite groups. So the answer happens to be actually no. So then you will say, what is the conjecture about? I will rephrase the conjecture. We'll modify. So the counterexample appears already in 73. There exists a group G of order 2 raised to 68 with nilpotency class 4, with exponent of this being 8 and exponent of G is 4. More examples have been produced after that, but this was the first one. So modified question. Let G be an odd order group. Does the exponent of H2GZ divide the exponent of G? The question, the conjecture is still open. So yes, so I'll tell you what all has been done and what our contribution is. So it starts, say, by M.R. Jones. He proves that the conjecture is true for P groups of class 2. When I say class 2, I mean nilpotency class 2. So let me, before stating the next theorem, I'll tell you what just a powerful P group is. If you do not know, anyway, we also do not know much about it, but still the definition at least So finite P group is powerful if either P is odd and commutator subgroup is contained in GP, or when P equal to 2, commutator subgroup is contained in G to the power 4. Now, Lubotsky and Mann prove of course they do other things, but they prove the conjecture for powerful P groups. Moravec proves the conjecture for metabelian P groups of exponent P. He proves the conjecture also for P groups of class at most 3. So now from 2, nilpotency class 2, we have moved to class 3. He also proves the conjecture for groups of class 4 and of odd order. He also proved the conjecture for P groups of class at most P minus 2. Okay. So I think I missed something here. So you can go a step further. So, I mean, there are 3 authors from Iran who proved it for class at most P minus 1. So it is also proved for P minus 1. And potent P groups, well, so let me write what potent P group is. So if gamma P minus 1 of G is contained in G to the power P, okay, such groups we'll call potent P groups. So for such groups, the conjecture is proved. Okay, so I have missed some hypotheses there. So in this paper, the most recent paper, Moravec proves the conjecture for P groups of class 5. Now, class 5 was the one that seemed that, I mean, no result was known about the conjecture, so it maybe was, people thought maybe at least maybe that would have been the first place where it may not have been true. So, but in 2019, he proves that it is square. He is not able to prove the conjecture, but he proves this result. So here is where, so in 2018, actually, I talked to, it was a Facebook chat, actually, I remember. I had asked him what is the situation, because he has been working on this problem for the last, I think, 10 to 12 years. So I had asked him what is the situation, and he says, at that time, he could only prove it is to the power 4 or something, or 5 or something, and he said computer evidence and gap shows that it is 2. So we started last May of 2018. We had got this fairly quickly, square actually. What he said can be obtained by computers, we had fairly quickly got it. But I had not noticed, but by January of 2019, he had already written a paper about it. But fortunately for us, we were able to improve a little further. So what we do is we prove the conjecture for finite P groups of class 5 with P odd. We also prove the conjecture for P groups of class at most P. So we have improved the last one, which is P minus 1 or P minus 2 was what was known. So we get that. And we prove the conjecture for finite P central metabelian P groups. And we also get the conjecture for this type of groups. I mean, it seems a little weird, but it's in a paper by Lawrence Wilson, who is a student of Glauberman. He introduced this kind of groups basically to study the power structure, meaning for such groups, the good thing, the key thing that we kind of use and other property is for such groups, this is nothing but the set of pth powers. This is the good thing about this. Similar for this type of groups. In fact, you take gamma m of G to the power G raised to P and you vary m P minus 1, it is also the same. This kind of groups were considered by Argenbright. So it includes the definition of powerful P groups, as you see, but it was considered by Argenbright about 20 years earlier. Yes? G, so that's good. So the question is the following. See, I said computer evidence shows that for class 5, this divides square. And we get that it is exactly the conjecture. So his question is, computer evidence should show that it is not square, but G. But see, that theorem is true also for P equal to 2. We are only considering, I'm not considering P equal to 2 at all. At some point, it will not matter, but I don't want to distinguish and say P is odd. Okay, yes. So this is the key fact. This condition you don't have to remember. Basically, it says that this GP is nothing but the set of P powers for this. So this is what we contribute. Now, another theme towards this problem is, see, if you have, this is much earlier now, so I think this is, at the moment, it's on the archive with that title. So it's a few months ago we put it. And earlier what was, the theme was, see, you're not able to prove the conjecture in general, so you take a group of nilpotency class C, and then exponent divides exponent of G. Now C by 2 doesn't make sense, of course, because it need not be an integer, so you put a ceiling, put the symbol ceiling there. Somehow I tried and it was not working. So put the symbol ceiling of C by 2 there, and that's what you need. So this is what done by Illes. Then Moravec did it if G is a finite P group of nilpotency class C, then exponent divides exponent of G to the power 2 times floor of this quantity, floor of log C to the base 2. Sambonnet, now again, so Nicolas Sambonnet is a student, was a PhD student of UVaL, and he proves, again here it is floor of this. C is reduced. Now that was C base 2, now he's doing C base P minus 1. So take the floor of this plus 1. So he proves this. Of course, I have not included C is again the nilpotency class. So you are assuming that G is a P group of nilpotency class C, and then you write that statement. In the same paper, we improve the first two results that I just showed, which is by Primož and Ellis, by saying that if G is a finite group with nilpotency class C, then and you set n is that number, which is C plus 1 by 2 and base 3, and if exponent of G is odd, forget this in between. This is a little general, which I will come to this construction once I go through the historical background and what is known so far, and then I will give you that construction. So what we are interested is, in particular, it says mg, I already said, it is h2, the Schur multiplier. It divides the exponent of g to the power n. So it improves Primož's and Ellis's result, but it quite doesn't improve Nicolas' result. It's still better in many cases than this. So towards that end, to perhaps to slightly improve Nicolas' result, we have the following. Again, you only look at the last statement because I have not introduced what G exterior G is. So here you have to take, again there it is ceiling, and for here also ceiling. So for us, n equal to 1 plus ceiling of this quantity. There n is ceiling of that quantity. And you get this result. So another result of another theme is if you take if you have the derived length. Suppose if you if the derived length of the group is d, then he proves that exponent of mg divides exponent of g to the power d. And if p is 2, then you have to add that factor of 2. So this is what he obtains. It's a very nice paper, actually. Some new methods, not the usual methods. He introduces some new methods to attack the problem. And so initially when we started, we actually had gone to his paper, but then suddenly we moved and used some old methods and some, yeah. So we get the same. In fact, we are not able to improve this. But we get slightly general, but he also gets something general. So I only stated his particular case. And so we also get the same particular case as he does. And, so now let me tell you what all this construction is. So at the moment I will, okay, now I'm confused. This is 22 minutes or left or left? No, this is almost halfway point, right? So it doesn't matter. Yeah, okay, so let me introduce the construction. I think less people are sitting here, so I better write. So another result, what I would say is, see, most of the results that are where the conjecture is proved happens to be under the subclass of the class of regular P groups. Most of this happen to be. And so one of the results even Sambonoy proves in one of his papers is that it is equivalent to proving the conjecture for regular, proving the conjecture for regular P groups is same as proving it for P groups of exponent P. And we do get the same theorem with our method. So if you want to prove the conjecture for regular P groups, you just have to look at P groups of exponent P. This is divides P. Exponent of Schur multiplier divides exponent of, huh? This is right. But this is actually, it seems, yeah, I will tell you more about it. It seems a little bit not so, yeah, strangely enough. One would think that this is easy, but, okay. So now I introduce a construction, and then I'll specialize, and then I'll define what this is, and I'll tell you what the strategy of the proof. Before, sorry, so this is, joint work with my PhD students, Ammu, Anthony, Ammu E. Anthony, and partly Ikoma. So I'm sorry, very good students of mine. They are sitting, one is sitting there and one is sitting. Yeah, so it is joint work with both of my PhD students. Sorry about. Is it? But okay, but they are here now at least. Yeah. So no, I didn't write at the beginning that this is joint work with. Yes, it is in the theorem. Sure, yes, but they are also here. Okay, so now I have to go back to the construction. So I have to. There is some symbols there, I have to define those symbols. So let's define in a general setup. So the setup for me at the moment that we have, for the construction, you don't need any finiteness. So the construction is good for general groups. So let G and H be two groups acting on each other. So basically I have map G to odd H, and I have another map from H to odd G. I will denote phi of G of H as G acting on H, and psi of H of G as H. This is notation, okay? Okay, so you have two actions by automorphisms, and these actions are said to be compatible So the actions are said to be compatible if the following condition holds. And a symmetric condition the other way around, which is H acting on G, acting on H1, has to be equal to HG, H inverse, acting on H1. For all H1 belongs to H, and G belongs to G. Okay, so this is what we need. At this point, one has to be a little careful. I should say it right away before somebody asks me. So, of course, I didn't say these are inside one big group. These are arbitrary groups, so this multiplication doesn't make sense, but what I mean by is like that. So, basically, once you have two groups acting on each other, the free group acts on it in this manner, and the action of the group on itself is assumed to be conjugation. So action of the group on itself is conjugation, and you have two actions, groups acting on each other. So once your actions are compatible, then you can form something called the non-abelian tensor product, G tensor H, which is a group. Generators are G tensor H, and relations are G1 tensor H is G acting on G1 tensor G acting on H, and G tensor H, and almost kind of symmetrical type of condition on the other side. G tensor H1 is equal to G tensor H, and H acting on G tensor H acting on H1. So once your actions are compatible, then you can form the non-abelian tensor product, and it is the group generated by this. I mean, the generators are given like that, and relations are given like this. Of course, the question is, you have to get, I mean, not all actions are compatible. So this is the difficulty here, but we still are in good situation because for application like this, you only consider one group, and we call the non-abelian tensor square, and all actions are conjugation. When all actions are conjugation, I don't need to check any of this because this is conjugation, it's already, everything is automatic. So then everything is okay. Otherwise, of course, you have to be more careful. You have to be, I mean, yeah. So now you have the non-abelian tensor square. Now let me say how we come to the problem. I mean, what is the connection? There is a little bit, you can compute some homotopy groups using this construction, but we will stick to homology, second homology in particular. So before going to that, let me just, there is one more which is what has appeared in the slides. So this is G exterior G. No, this is not white. Which is G tensor G modulo the subgroup generated by G tensor G. So this we'll call the exterior square, just like usual. And you get the exterior square. And now I want to define some maps, and then we'll see what is the connection of the Schur multiplier to this construction. So there is a map, the kappa map, to the commutator. Let's write it like this, which takes G exterior H to GH. Its kernel is also interesting. It gives some homotopy groups, but for our purpose, we need this. This map, because G tensor G goes again, it goes to 1, there is an induced map on G exterior G, the same map, and the kernel of this map is what is interesting for us. This is a surjective map, and the kernel happens to be, it is proved that the kernel is the Schur multiplier. Okay, so this is MG. This is an old result of Claire Miller, I think in the 50s or something. So this is the Schur multiplier. So now you know what that G tensor G is and G exterior G is. Okay, good. So now let me tell you maybe a few words about how one can go about proving some of this. So first I will try to see for class P, okay? Once you have class P and then you want to prove the conjecture for class 5, what all you have to do is, so groups of class at most P, so which includes class P, once you prove that, then I want to prove class 5. What I have to prove is only prove it for the case P equal to 3, because P greater or equal to 5 is automatic by that result. So first I will show what is the general idea, and then we'll go to this general idea. I mean, it's a simple, trick is very simple. So let me tell you how perhaps one may obtain class P. To get class P, we again go back to an old result of Schur, which is very well known, and I think there are several proofs for this, that it says that if the center has finite index, then the commutator subgroup is finite. There is an old result of Schur that if the center has finite index, then the commutator subgroup is finite, and then there is a whole game of what is the function, in what function of this, if it is finite index n, then what function of this is that order bounded by n, etc. So what we have to do is get an analogous result, but slightly more general. So you have to obtain what it means to be general. So you should say, since we are talking about exponent, it's no good if you just do this, because this is now you're talking about the order. So now you should talk about a new, say, statement saying if exponent of a group is, say, let's exponent divides n, then I want to prove that the exponent of the commutator subgroup divides n. Let's say this is a new statement. So we make a statement, if exponent of this divides n, then exponent of the commutator subgroup divides n. Well, if you can prove this in generality, then I would say you are done with the conjecture. You just have to prove this new theorem, kind of, which is analogous to Schur's original theorem. But we were not able to prove this theorem. Perhaps this theorem in generality is false also. I have not looked at examples. I didn't think about it much. But what you can prove, I mean, in general, in some sense, we did think, but we didn't get it. So what you can prove, what we could prove, is if the group, it's a P group of nilpotency class, say P plus 1, then this theorem is true. Once you get this theorem, then you get, as a very easy consequence, directly the conjecture for class P. All the other results were already till p minus 2 and p minus 1 was known. So that all those results are included in our result. So the idea is to prove a new statement that if exponent of divides n, then this divides n. If you get this, then you get the conjecture. So this is slightly general than the classical theorem of Schur, which says the order, and then the order is finite. Instead of saying that, you say something like this. And the way to go from here to the conjecture is you take a Schur cover, and then it's just two-line proof. So this would be the key step. Okay, once you get that, then you play with some so let's go now. Let's assume that we have proved this theorem and we have proved the statement for class P. Then how to go to class 5? As I said, for class 5 now, it only suffices to prove for the prime P equal to 3. Because P equal to 5 and above is proved by this result. So P equal to 3 is the only case, and then you consider some sequence like this. And then you estimate what the size of this would be, and what is this? This is already exponent 3. And then this somehow somebody else has done it, so you get it for, this is 3, so all you have to do is, this is 3 raised to n minus 1. If exponent of our group, G is, exponent of our group G is 3 raised to n, suppose, then this you will prove that this is 3 raised to n minus 1, and this you will prove, already somebody proved it, that this is 3. So so then what you do is with the exact sequence, it says that exponent of this divides the exponent of this times the exponent of this, and you get 3 raised to n exactly. And all the results, whatever has been obtained so far, we were able to obtain in the paper, but the tricks are almost similar. You just vary. So basically the sequence looks like this, you see. And the game is to, given a particular problem that was known, if you want to prove it, you select this n properly. So in this case, it happens to be this. Sometimes this n has to be, say, gamma of the nilpotency class of G. You put that. And when you go down, you have gone down by the nilpotency class 1 less in this group, and this gives the conjecture by induction somehow. So this is the this, I would say, is the gist of it. And I have 5 more minutes. So, of course, there are some computations to do this, but this is not illuminating if I even show any of this. So I think at this point, I would leave it like this and maybe make a few remarks, which is, so I don't want to say, because Primož has been doing this a long time, but after doing this, it felt like he feels that the conjecture is perhaps false. I feel that the conjecture is perhaps true, actually. But one thing I can certainly, I mean, somebody can maybe disprove me, but I feel that you can at least prove this. This should be very easy. I mean, we have not been able to get, because we are now already got very tired of the problem. We worked for a year. Now, after a short break, maybe we come back to this, and which is this, and I will tell you why we believe this. So you can show that the exponent of Schur multiplier, this I think for a P group is P times exponent of G. In the latest 2019 paper of Primož, he suggests that the conjecture should be reworked into exponent of Schur multiplier divides exponent of G to the power square. I would want to say that you don't need to go square. P times is good enough, and I think already my PhD student has written it for 7. We can go easily up to 13. We have not written it down, but till nilpotency class 13 at least. I think even further you can go. But the problem is that, see, every time the computations is similar, but with, I mean, you would say mutatis mutandis goes, but then you see you have to write 25, 30 pages, and this is not. So a new idea should be there, which attacks this at one shot and kind of gets that. So I feel the conjecture perhaps is still true for, should be, yeah. But even this for a definite one can obtain is what our feeling is. So I think I'll stop here.